Alright everyone, so today you're going to have your video lesson on 3.5, which is derivatives of trigonometric functions. So before we get into any of the derivatives, we're just going to start by graphing the sine and cosine graph the same way, or sine rather, same way you did in pre-calc or trig. We have our unit circle, and then we have our x-axis in radians, and then these can correspond to the unit circle value. So of course you know that this is 0 degrees or 0 radians. This is pi over 2 radians. This is pi. This is 3 pi over 2. And then back around is 2 pi. 0 radians and 2 pi are the same thing. And then we also know that the coordinate system goes cosine, comma, sine. So cosine is our x, sine is our y for the values on the unit circle. So first thing we're going to do is we're going to try to plug 0 in here. So we're going to take sine of 0. And sine of 0 is just, if we go here at 0, it's cosine comma sine. So sine of 0 is 0. So we're going to start at the origin. And then we're going to do sine of, you don't have to write all these out. Once you know how this graph looks, you don't need to do this every time. Sine of pi over 2, which is sine of 90 degrees. So if we look at 90 degrees, the coordinate is 0, 1, and we know that y corresponds to sine. So here we're at 1. And then we just keep going through this process. Sine of pi, right here. I know I don't have the hovering mouse, so it's hard for me to indicate what I'm talking about, but we're going to do sine of pi right here. So if I look at pi, sine of pi, sine is going to be the y coordinate, so it's going to be 0 again. So you're going to notice that it always goes back to 0 every other coordinate, so you can test that out, but every other coordinate always bounces back to 0, and then it has a pattern. So now let's try 3 pi over 2. So if we look at 3 pi over 2 right here, sine is our y coordinate always. So of course it's going to be the coordinate 0, -1, which is going to be down here. So this right here is one full period of sine, and then everything else is just going to be a repetition of that, because there's no manipulation on the period, or there's no phase shift or amplitude change, because we're just looking at the sine parent function. So then from here we can just repeat the same process. So we can just assume, and if you wanted to verify it, you can use your graphing calculator and do sine of this value. Make sure you're in radians if you do so, but you can verify that it's 1. And then this is going to go down to negative, and then we're just going to always bounce in the same periodic pattern. Oh, I made a mistake on that one. There we go. So this is what sine looks like. I'm not going to go in as much depth as I would in a trig class to explain all the details, but I know you've all seen this before. So here's where we're getting into the calculus aspect of it. So the derivative of sine is actually equal to the cosine graph. But other than me just telling you that, I want to show you why that's the case. So here's the reason. We know that the derivative of any graph is going to be the slope of that graph, right? So we're going to graph it as if we're finding the slope at each of those points. So I'll show you what that's going to look like. So if we look at this graph, we're going to use this graph to model. This is going to be the slope of this graph above us, okay? So if I look right here at 0, as you can see, if we take the slope by drawing in a tangent line, the slope is 1 at 0. So we're going to go 0. And then if we look at pi over 2, as you can see, the slope here is 0. Anytime that you have that shape where we flatten off, of course the tangent line is going to have a slope of 0, so that slope is going to be 0. Now you're going to notice that that occurs here. It occurs at pi over 2. It occurs at 3 pi over 2. It occurs at 5 pi over 2. It occurs here. It occurs here. It occurs here. All of those points are going to have a value of 0 on the derivative graph. So we have a 0 here. We have a 0 here. We have a 0 here as well. 0 here and 0 here. And now we can look at the other ones. So all the ones that have this positive slope like this one does are here, here, and here, a positive slope of 1 at those 3 values. So at -2, also at 2 pi. And then all of the ones that have a -1 slope are here, 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 and here. So those are all going to be at -1. So that's how you can graph the derivative of it. And you're going to see that once we graph this, it's actually just going to be the cosine function. We can graph the cosine function the same way we graph the sine function by plugging in values. So once I graph the derivative of sine, you're going to see that it's clearly just cosine. And that's the reason that the derivative of sine is cosine. But you can actually just commit this rule to memory because you're not going to have to do the graph every single time. I just want you to understand why it is what it is. So then next, the derivative of cosine is actually just negative sine. Okay, so I'm going to prove to you why that is, taking this graph and finding the slope of it. So same rule applies. Everywhere that we have the slope of 0, which is all these points, we can graph our graph at 0 there as well. So here slope is 0, because remember this is the derivative of that graph. Slope is 0 here, slope is 0 here, and here, so every other. And now we're going to look at the slope of the line. So all the positive slopes are here, here, and here, the +1 slopes. So we're at +1 here, we're at +1 here, and at +1 here. And then all of the negative slopes are at these 3. And then if you go to graph this, you end up with something like this. And as you can see, if you compare these two graphs to each other, the first graph and this graph are just the same thing, but one of them is reflected over the x-axis, which is the indicator of it being negative. So we know that the derivative of cosine is negative sine, the negative sine graph. So if you were to put any of these graphs in Desmos, you would see that to be the case. So derivatives of sine and cosine play a key role in describing periodic change. All right, so on to the next page. So it says here, we're going to go ahead and find the derivative of tan of x. So once again, this is going to be one of those ones that you're going to commit to memory, but we can essentially use the identity, the fact that tan is equal to sine over cosine, to prove this. So we want to find the derivative of sine over cosine to find the derivative of tangent, because we know tangent is equal to sine over cosine, right? So we have our quotient rule. We're going to use that here. So this is my numerator, which is f of x, and this is my denominator, which is g of x. So then we know that the derivative of sine, which we learned on the last page, is cosine. And we know, I'll do g of x in green. We know that the derivative of cosine is negative sine. So that's just taken from the last page of the notes. Now we can just plug into the quotient rule formula. So it's going to be g of x times f of x, f prime of x, minus f of x we don't really need the parentheses there because we're not separating anything, times g prime of x. And that's the numerator. I'm going to simplify this before I write that denominator, and I didn't forget about it. So this is going to become cosine squared of x. A negative times a negative is a positive, sine squared of x, and this is all over our denominator squared, so cosine of x squared. If you remember back to when you learned about trigonometry, this right here is a trigonometric identity. I don't know if you remember which one it is. The rule is that cosine squared plus sine squared of x is just 1. So this whole top is going to become 1, and then we have 1 over cosine squared of x. Well, cosine's reciprocal is secant. So if we take the reciprocal of this to get it back into the numerator, this is going to become secant squared of x. So that's actually the derivative of tan. So that is another one you're going to want to commit to memory. You're not going to want to do that every time, but they're free. I mean, you could. So these are the other trigonometric derivatives. We have secant derivative, we have cosecant and cotan. So now you know all 6 of them. The main ones you're going to want to remember are sine, cosine, and tangent, but these ones also come up in your homework. Now I will mention that your homework problems are a little bit more difficult than when you're going to see on a test or quiz, so please don't be discouraged by that. Okay, so the next one says find the derivative of this. So as you can see, we have the product of two things. We're going to have to use the product rule. So we're going to call f of x going to be our first item, which is x squared. G of x is going to be cosecant of x. And then we have to take the derivative of each of those. So we know the derivative of x squared is 2x. And we know the derivative of cosecant, I'm just going to use it from right from the notes, is negative cosecant of x times cotangent. So now we can just use our product rule. So the product rule says f of x times g of x, or g prime of x. So you're going to notice a lot with these that there's times where simplifying it's going to be beneficial, other times not so much, but we're not going to simplify here. We're just going to leave it as is, times g of x, unless it really simplifies, times f prime of x. Guess I'll do that in blue. And then we're here, so we could factor out a x and a cosecant, but we're just going to leave it the way it is. This would be the derivative. So when you're doing calc, always make sure that you're not oversimplifying if you're not asked to simplify. So example 4 says, find the derivative for this one here. So to find this derivative, I'm going to the first part is easy. It's just the derivative of 5t squared, which is going to be 10t. But it's this part that we have to focus on because this part is going to require the quotient rule, right? So that's going to be minus, and then we have to do the quotient rule over here. So this is going to be f of x is our numerator, or f of t rather. F prime of t, I'll switch it to t, is going to be the derivative of sine, which is cosine. So I'm just, to clear up, I'm doing the product rule for this because we can't the quotient rule, because we can't take the derivative of this without using the quotient rule. And then our denominator is going to be called g of x, or g of t. 1 plus cosine of t. We know that the derivative of 1 is just going to go away, so we really just have the derivative of cosine, which is negative sine. So now we can set up the rest of the derivative with the quotient rule. So if you forget the quotient rule, it's right up here. It's g of x. And I always mix up x's and t's because we're always interchanging them, times f prime minus f of x times g prime. So this one's going to be pretty easy to simplify that numerator all over g of t squared. So I'm not going to really deal with the denominator too much. Okay, so this up here is going to become sine squared, right? And this is going to distribute. So you could actually leave it just like this, but you could, if you wanted to, if the question was a multiple choice, you could go ahead and distribute this out. And then here, this is going to become positive sine squared. So I'll at least simplify it a little bit. 10t minus This is going to be 1 times cosine, and then it's going to be minus cosine times cosine, which is cosine squared. And then it's going to become a plus sine squared, because a negative times a negative, and then sine times sine is sine squared, all over 1 plus cosine of t squared. Now what you're going to notice right here is this is actually the trigonometric identity, so I can actually replace this whole bit with 1. So I don't have room to do that, but it could end up being replaced by a 1. So that is important, because if it's a multiple choice question, you have to be ready to make sure you can modify it accordingly to match the multiple choice. So that's the thing with derivatives that's really important, is the many different representations. Next one says find all the x values on the interval where f of x equals x plus 2 times sine of x has a horizontal tangent line. So horizontal tangent line is going to be anywhere that the slope is 0. So anytime you see that in this class, horizontal tangent line, we know the slope is 0. Okay, we know the derivative is slope. So what we need to do whenever we see a tangent line problem is we need to take the derivative, of course. So f prime of x is equal to this derivative. Derivative of x is 1, plus the derivative of 2 times sine of x is just 2 times cosine of x, because the derivative of sine is cosine. The coefficient doesn't affect the derivative. So now that we have the derivative, we know that we need the derivative to be equal to 0. So we need to find the variable value that makes it equal to 0. So we're going to set this equal to 0. And then we're going to solve for the variable. So to do that, we're going to subtract 1 on both sides. That's going to give you negative 1 equals 2 times cosine of x. Divide by 2. And we get cosine of x is equal to negative 1/2. So we need to find all of the degree or radian values that are going to make that statement true. So I know that cosine of 60 degrees is equal to positive 1/2. That's a trigonometric exact value. But we can look here and actually just look at the unit circle and figure this out. We know that the unit circle is always cosine comma sine. So we're looking for the x-coordinate to be negative 1/2. So we have it here. Make this a little smaller. We have that here. We have that here. And I believe that's it, because remember, cosine is positive in these two quadrants, if you remember that back from your trig rules. So for that reason, these are the only two x values that this would be true for. X equals 2 pi over 3 and x equals 4 pi over 3. And we just make sure we answered the question. It just says x values. It doesn't say to find the y coordinates that correspond with them. Had it asked for that, you would have to take these x values and plug them back into the original function, just like we always do. So just because we're doing trigonometry doesn't change any of the rules that we use to find tangent lines. We just evaluate them a little bit differently. So this one says a particle's distance from the origin is modeled by the function where t is measured in seconds. Determine the velocity at pi seconds. So we know when we see that terminology velocity, we know we have to take the first derivative to find the velocity, of course. So we're going to take the derivative. The derivative of sine is cosine, so it's going to be 2 times cosine. And the derivative of cosine is negative sine, but since it's already negative, it's going to become a positive sine. Now they want to know the velocity at pi seconds, so we're just going to plug in pi. So this would be a more typical type question I'd ask you. These two right here are more like what I would ask you on a test or quiz, nothing really complicated. Now we just evaluate. So if you still don't know your trigonometric exact values, you have a calculator, so it's all good. Cosine of pi is negative 1. Sine of pi is 0. That's where I got those from. So the velocity at time pi is equal to negative 2, and this is meters per second. So if you're wondering how can time be pi, well, pi is just a number, right? Pi is approximately equal to 3.14. So at 3.14 seconds is what that means. So you have to think of pi in different types of ways. You have to think of it as a radian, but also keep in mind it still represents a number. It's just an easier way to say a number that's kind of messy and has a decimal. So that's it for this. Go ahead and try the homework. If you get a really hard derivative, just leave it in its least simplified form. That's okay. And I'll see you guys soon.